Welcome back, and off we go. Aromatic cations, as we saw before. We could have had an aromatic cyclopropene if it was a cation, and here are the reasons why. We have a similar story to if we replace this carbon that has a cation with a boron, which is naturally sp2, so it has a p orbital that can resonate, then we would get the story, same story here over here, except boron started neutral, became an anion with a fourth bond. This cation here is one of my favorites because I worked a lot with that in graduate school to do a synthesis. And it has 7 resonance forms. It's the Cyclohepta Triennial cation, also known as the Tropylium cation. You don't need to know that name. Although there's a whole class of drugs called tropane alkaloids that all have that size ring. Cocaine is one of the members of that family, and atropine is another one. In fact, atropine has trop in its name, and that is a heart stimulant. And 7 resonance forms. Does it follow all the rules of aromaticity? It sure does. We have 2, 4, 6 pi electrons. We have 7 atoms, all with p orbitals that can resonate in a circle. And I think in a nutshell, that covers everything. And earlier, I asked you the hypothetical, how could you have an anion that's aromatic? Well, here's an example down here. If you start with this molecule, which is not aromatic because of the sp3 nature here, so that can't resonate, and we have the wrong number of pi electrons. We have an acid here with a pKa of 16 and a bold statement. This is the strongest hydrocarbon acid that we will have in this course. It's lower than an enolate even, which was 20, even though that's not technically a hydrocarbon having oxygen in it, but you are removing hydrogen from carbon. Strictly hydrocarbons, we've got this molecule, we've got alkenes 45, alkynes 25, and alkanes 50. This is much lower than all those numbers. Good test question. Why is the pKa of this molecule 16? And the answer is because the conjugate base with 6 pi electrons and every atom sp2, when this thing rehybridizes, is an aromatic anion. And aromatic stabilization is a big deal. On our next page, we will even summarize how big of a deal numerically that is. One of my favorites, Azulene, which looks like a nonpolar molecule that you'll see right here. Azulene has your favorite ring size 7 glued to a 5. And it's got double bonds like this. And I didn't do it right. Okay, one of my favorites, but apparently need some more practice with it. There we go. Okay. Now, the multiple questions can be asked. One, why is it aromatic? It has 2, 4, 6, 8, 10 pi electrons. Can you solve 4n plus 2 equals 10 with an integer on n? And by the way, that's the only meaning of n. I'll have students, even this semester, ask, what does n mean? N is a hypothetical integer that if you can solve 4n plus 2 equals an integer and match the number of pi electrons in your molecule, then your molecule has the right number of pi electrons to be aromatic. That's what n is. So count the pi electrons is step 1. 2, 4, 6, 8, 10. Can you solve 4n plus 2 equals 10 with an integer? Answer, yes. N equals 2. 4 times 2 plus 2, 10. So it has the right number of pi electrons. Every atom here is sp2. Every atom's in a ring, and we can resonate around the rings. So we have all the rules followed. And another favorite question is, why is this molecule that looks totally non-polar, doesn't have a single polar bond in it, why does it have a bond dipole when they did an experimental test on it? And the answer is, if you draw the other resonance form, where you resonate away from ring size 7 towards ring size 5, you can generate this resonance stabilized diion. Spends most of its time back there. But this structure I'm about to draw is still aromatic, even though it has charges. It has a lone pair here, double bond there, and double bond there. Double bond didn't change here. This one's here. We got a cation here. Have an anion up here. That would give this thing a net dipole. A net dipole pointing away from the cation towards the anion. So yeah, azulene, a somewhat polar molecule, surprising for its nature of just having C's bonded to H's. And moving on, how big of a deal is aromatic resonance stabilization? Well, let's look at some old stuff and integrate it with some new stuff. If you did the experiment where you reduced this alkene using hydrogen and some transition metal catalyst, I think your most common ones so far have been platinum and palladium. Platinum by far most common, but nickel's in the same area on the periodic table, central in the D block, and it's a common catalyst for the same reaction. It's a specially formed version of a refined version of nickel called rainy nickel, named after a person, and it's very porous and it has a lot of surface area because of that. And it will reduce, and you'll generate a normal 360 kilojoules per mole of this molecule. Exothermic, why? Good question. You should be able to tell me it's exothermic without me even giving you the delta H by comparing structure stability with pi electrons to structures that have no pi electrons. And just remember that pi electrons are less stable than all sigma. So we expect this to be lower in energy right here, and both of these to be higher in energy because they have pi bonds. Now, to do the math appropriately on this one, I would have to do H2 and nickel, and I do the experiment, but this thing does not like being reduced. This is an extreme circumstance. 20 atmospheres pressure requires very special equipment, very thick steel wall containers so that they don't explode. And this experiment, this is how the majority of cyclohexane is made for lab use from benzene. Benzene is pretty much a waste product from the petroleum industry. We can get it for pretty cheap. And you only get negative 208 kilojoules per mole. And we're doing the same product here. And what happened was I really did 3 of these and 1 of these, and I got the same number of pi electrons being reduced, but I did not get the same amount of energy back. I got a lot less out of this reaction than I got out of this because these pi electrons are much more stable than this pi electron here. Why are they more stable? They can resonate in a circle with the right number of pi electrons, and it's called aromaticity. Aromatic molecules, pi electrons, are more stable than molecules whose pi electrons are not aromatic. And that difference in energy is called the aromatic stabilization energy, or we can call it resonance stabilization energy here. And it accounts for a difference of 152 kilojoules per mole when we're talking about 6 pi electrons. That's benzene's number of pi electrons. Benzene's pi electrons are 152 kilojoules per mole more stable than the same number of pi electrons in a non-resonating molecule. That's what that says. So if we wanted to predict how much more stable naphthalene's pi electrons are than normal pi electrons that are not resonating, we would have to realize first we have 10 pi electrons now enjoying the resonance stabilization energy instead of just 6. So I would expect 10/6 more resonance stabilization energy. 10 for naphthalene, 6 for benzene. There's benzene's number. And I get this result as a prediction for resonance stabilization energy. The experiment was done, and we got almost exactly the same results, showing our theory's pretty good, using 152 kilojoules per mole as the predictor for stabilization energy when you have 6 pi electrons. It works with pretty good predictive ability. Moving on to anthracene, you almost get the same predictive ability, 14 pi electrons now instead of 6. And your result that you predict is within 2% of the actual. Phenanthrene is a little more off, but still pretty good predictor. Something to do with the geometry here. That would be a good study right there. It's probably been done. So that gives us resonance stabilization energy in a more quantitative sense. And let's see, we'll finish this segment. We don't have to talk a lot about nomenclature because we've already looked at nomenclature of aromatics. I told you to look at it when we first studied para-toluene sulfonic acid. Do you see it on the page? I do. We see para-toluene sulfonic acid here. And this, everything on this in this box is a di-substituted benzene. And that's when we're allowed to use the ortho, meta, para system for naming di-substituted aromatics. That's what we have right here. Here's your generic di-substituted aromatic with one group already on it. And the names would be ortho for the next group being here or the same distance away on the left. If there was another group in this position, two carbons away, we call that the meta position. If there was a second group on the position as far away as possible, we call that the para position. We have examples of ortho, meta, para here, starting with our friend para-toluene sulfonic acid. We could have named it another name if you wanted. You don't have to use ortho, meta, para. You could have called it 4, and you don't have to use toluene either. 4-methyl benzene. Remember how to name acids sticking off of rings when they were carboxylic? We could have said benzene carboxylic acid. We could have. Now, when it's a sulfonic acid, it's the same story. Benzene sulfonic acid. Separate word for the acid sticking off the ring. I think you like the name HOTS a lot better. It's a lot shorter. That's another name. This one has 3 names. Remember those molecules you have to know? We've got 2 of them here. We're supposed to know the name of benzene with an alcohol. It's called phenol. So phenol has an aldehyde stuck off of it on the 3rd position, and that's the last name. Phenol 3-carbaldehyde. Or you can name it after this molecule right here, benzaldehyde, and say there's a hydroxy group on the 3rd position, or say on the meta position. So there you have it. In this one, you can recognize the name toluene or structure of toluene right there. And two of the names say there's a ethyl group 1 carbon away, or also known as ortho. So those names are all acceptable. Over here, we are reminded that in these molecules, we're not going to be using ortho, meta, para over here. These are hetero molecules, these three heterocycles, we call them. And the thing you need to review for that is the heteroatom, nitrogen for pyridine, oxygen for furan. Heteroatom is position number 1. We knew that back when we studied chairs and cyclohexane and glucose. So that's position 1 and that's position 2. This is position 1, 2, 3, and positions 1, 2, and 5. So that explains these names. Nitro, and please learn this now. This group here, NO2, very common group that we're going to use extensively on this next test and forever from now on. Nitro Group is a popular group found in a lot of pharmaceuticals. So we should know that it looks like that in its shortest form. And we should know at the drop of a hat how to draw its Lewis structure, which is kind of unique. It's got adjacent plus and minus ions. It does qualify as an ylid in that regard, but it's a resonating ylid. So we don't think of it as an ylid in terms of its reactivity. So learn the nitro group. It is an important group. And then we're going to finish this segment by giving 3 names for this molecule. We can go straight up with just calling it benzene, which is kind of boring. Then you just have to name the 2 groups, hydroxy and dimethylamino. So we'd say 1 hydroxy. I didn't even use ortho meta para. This would be para, by the way. One of my names will have para in it. 4 dimethylamino. Benzene. Or you can use the green name and call it a phenol. And that would be P dimethylaminophenol. Phenol. Or you can go with his other name, up to there is called aniline. Aniline. And this has a hydroxy on 4. And 2 methyls on the nitrogen. You don't say amino. You've already got the amino covered with aniline. So 3 names. And I think that's a good spot to stop, especially since we have a blank page facing us. And I will see you on the other side of the break.